Okay, so now we will start the mathematical modeling. Before that, we can have a general principle for modeling of the plants here in process control. Okay, so the general principle or the standard principle for in most of the plant most of the mathematical model which we use, that is principle of conservation. Okay, so here this will be rate of accumulation is equal to rate of input minus rate of output, rate of output plus rate of generation. Rate of accumulation will be equal to rate of input minus rate of output plus rate of generation, right? So if we have only mass accumulation, no product is being generated, then this rate of generation will be 0. We will have only rate of accumulation is equal to rate of input minus rate of output. Okay, so now we will start the first model. This is CSTR. CSTR stands for continuous stirred tank reactor. Okay. So CSTR is one of the benchmark examples of process control which we will use repeatedly at many places in process control for studying various things. We will study this. We'll use this. So first we will draw this CSTR. So obviously there will be a tank because this is tank reactor. So we have a tank here. And because this is a continuous stirred tank reactor, so there will be a stirrer also. There will be a stirrer also in the tank. And this is the liquid, and we have liquid coming here inside this tank, and we have liquid going out. So this is the outlet, and here we have coolant in and coolant out. So here we are providing coolant in, coolant out. So now we will write all the variables. So this is a tank, and this tank is having a jacket, outer jacket. This tank is with jacket. We have a tank, we have jacket, and here we have the inlet flow rate is Fi. Fi is the inlet flow rate. Then we have temperature of the inlet, the reactants which are coming inside. Temperature is Ti, and the concentration of the reactants are CAI, right? So Fi is the flow rate. Fi is the flow rate of the reactants which are coming inside this tank. Ti is the temperature, and CAI is the concentration. So shall I write it? Concentration CAI, flow rate Fi. Flow rate and other things we have seen already many times while you were studying that Searles tank. Flow rate and temperature. So these are at the inlets, and similarly at the outlet we have flow rate F, concentration Ca, and temperature is T at the outlet. And inside the tank also the temperature is T, and here the coolant flow rate is Fc. So in throughout the process control we will use variable F for flow rate, obviously T for temperature, and Ca or something C will be concentration. So Fc is the C stands for coolant. Okay, I input, and some books you can find also that F naught for output, or F is also okay at the outlet. So Fc is the flow rate of coolant, and Tci is the temperature of the coolant. So Tci, and here we have here we can write Fci. Yes, Fci, and here we have at the outlet we have Fc. Here we can write FCO, there is no issue, and then PCO is the coolant out. This is coolant in, and here we have coolant out. Okay, so Fi, F, FCI, FCO, these are the flow rates. All the T's are the temperatures, all the Ca are concentration, right? So as we know that when we do mathematical modeling, we take some assumptions. And why we take assumptions? To simplify the modeling, right? We take assumptions. To simplify the modeling. So what will happen if we do not take assumptions? So with this we will see by the first assumption. So the first assumption, we are taking that there is a perfect mixing in the tank because we have a stirrer here. So we are considering that there is perfect mixing in the tank, and so the T is the temperature inside CSTR, and this is equal to the outlet temperature. So throughout the tank, the temperature is constant, and the same product is going out. So the temperature is also T. So what will happen if we do not consider this? So in that case, if we, because obviously we know that the temperature throughout the tank will not be constant. So at this particular point, temperature will be something else. At this particular point, temperature will be something else. Here, the temperature will be something else, and there will be number of points with different temperatures, right? There could be more than 100 or infinite points with different temperatures. So if we do not consider perfect mixing while doing this mathematical modeling, so we will have number of variables. We will have so many variables that the modeling will be very much difficult. So that is why we take assumptions. right? So that is why we take assumption. So this is our first assumption, that throughout the tank uh, there is perfect mixing. The second assumption for this, we'll take that the reactor is perfectly insulated. So what does it mean? That there is no heat loss to the surroundings. Sorry. So what I have written? Yes, I have written here that the reactor is perfectly insulated. That means there is no heat loss to the environment, to the surroundings, right? So because we know that there will be heat loss, right? And how much that heat loss will be, what is the current environment temperature, which side of the tank the temperature is, how much. So to avoid this, to simplify the modeling, right, we are considering that reactor is perfectly insulated and there is no heat loss to the environment, to the surroundings. Okay. The fourth assumption is that, no, not fourth, third. The third assumption will take that the coolant is also perfectly mixed. Right? We are considering that the coolant is also perfectly. Okay, I'll write it again. The coolant is perfectly mixed in the jacket. Right. So that means that this means that at all the places, here, at all the points, the coolant temperature is same, right? We are considering that coolant is perfectly mixed, so that at this particular point, the effect of coolant will be same to this. So that is why we are considering coolant is also perfectly mixed. The fourth assumption, this we will take that we will not do any energy balance for because in CSTR we are providing some reactant. So before that we should write this is okay. There is no issue. We have written no energy balance for jacket. So we have you can write it before all these, that this is a simple exothermic reaction, first order reaction. So that means heat is coming out of the reaction. Exothermic, heat is coming out. So to remove this heat, we are providing coolant. So for removing heat, we are providing coolant. So
So what
after
is jacket here means?
this is the jacket, the outer this, right? This was
Okay.
a tank. I mean, when we were studying that surge tank, this was the tank, right? There was no jacket in that. This was only one. We have drawn only one. So here we have the double structure is there. So this is the outer jacket. We are providing coolant in the outer jacket. Okay. So yeah. So here we
So what
have
is exothermic first order reaction?
this. You should tell me that what is exothermic first order reaction. एक्सोथर्मिक तो अभी जस्ट आई हैव टोल्ड यू, सो शायद आप कहीं और आपका ध्यान था. ओके, सो आप इसको गूगल करिए, देखिए. सो दिस इज मे बी 12th और 10th आपने पढ़ा होगा, व्हाट इज एंडोथर्मिक, व्हाट इज एक्सोथर्मिक. Okay, so ये आप देखिए, this you should tell me. Okay, so this is simple exothermic first order reaction, and here, okay, yeah, and this to remove the heat of exothermic reaction, we are providing coolant, and then we are considering that coolant is also perfectly mixed. You should also tell me that what is endothermic reaction. Okay, so coolant is perfectly mixed, then there is no energy balance for jacket, then reactor is perfectly insulated. We have some other assumptions also, that liquid density is constant, liquid density and heat capacity are constant. Okay. So liquid density is simple, that density of the reactants which we are providing to the tank. So this variable we are considering as rho. Rho is the liquid density, and heat capacity is Cp. Cp is the heat capacity. Okay. So Cp is heat capacity, and so when we will provide the heat to any particular object or material, the temperature will increase. When we remove the heat, temperature will drop. And we know the relation, this relation, that we have studied this also, that Q is equal to C delta T. This C will be the heat capacity. So heat capacity is the amount of heat required to raise the temperature of a material or object by 1 degree. Okay. So heat capacity is constant here. So by which you can increase the temperature of a particular object by 1 degree, that is heat capacity. So liquid density, rho, and heat capacities are constant here in this. So we have total 6 assumptions here. Okay. So now we will start. So the modeling. So the first equation we will write, that will be overall mass balance equation. Overall mass balance equation. So this will be, because we are writing only mass balance, so we will have this rate of mass accumulation is equal to rate of mass rate of input, rate of mass input, and write here rate of mass accumulation is equal to rate of mass input minus rate of mass output. Right. So now we can write the equation. So here, yeah, there is one more variable. The volume of the liquid inside this tank is V. Right. So we have these variables. V is the volume, and T and other variables. Okay. So now we have to write the rate of mass accumulation. So because this is the rate, so there will be d by dt, rate of mass accumulation. Now we have to write m. So we do not have m mass variable here, so we can write it using the variables which we have here. So let me find rho. Rho. Yes. So we can write this mass as, we can write V into rho. V into rho can be written as mass. So rate of mass accumulation is V into rho Then rate of mass input, we have the flow rate. So Fi into rho minus rate of mass output. So the outlet flow rate into rho. And why we are writing rho, rho, rho everywhere? Because we have already considered that liquid density is constant at the input, at the output, and inside the tank. That is why at all the places we have written rho. So rate of mass accumulation, here V is the volume, V is the volume of liquid or the reactant inside tank, inside the reactor, right? So we have this d by dt of V into rho is equal to Fi into rho minus F into rho, because rho is constant. So obviously this rho will come out, and rho will be cancelled out, because rho is constant, rho can come out, and all the rho will be cancelled out. And what we'll have left here, so dV by dt is equal to Fi minus F. So this we will use at many places, the mass balance equation of CSTR. CSTR is what? CSTR is continuous stirred tank reactor. So this is the mass balance equation of CSTR. Okay. So here in this tank we have only one input stream, only one outlet stream, and if suppose we have more than one input, more than one uh, suppose n streams coming, and suppose m number of streams going out, then how we can write the equation? Here I need summation, yes. Okay, so for more than one number of streams coming in and more than one number of stream going out, we can write this as here we will write rho, because we do not know, because the density of different streams could be different. So that is why rho is the density of the liquid inside the tank. Here, because there was only one stream coming and one stream was going out, so that is why we had considered rho as constant. But if there are more than one streams going in and going out, then the density cannot be constant. So that is why, just a minute. Okay, so d rho v by dt is equal to, this we can write as, now I need summation. So this we can write as summation I is equal to 1. Oh, what happened? Why it is so big? What happened? Something happened, I don't know. So I is equal to 1 till n. Oh, you can write rho I rho I fi. I don't know what happened. Rho I fi, and then minus
So,
yes,
sir, Fi is already a notation, no?
fi is, yeah. So we can write this j. So this will be Fij. This you can write j. So this will be Fij. Okay, then minus. Let me copy this. So here we can write m, because there are m number of streams going out. So m, and we can remove this j. So this will be good, or we can write here some, suppose k is equal to 1 to m. So f of k. So in this way we can write, if we have more than one incoming and outgoing streams, then we can write this. So this will be the mass balance equation for CSTR.
Thanks for watching. Master Control. Master the future.